about standard candles as distance measuring tool. The distance modulus is formally defined as mu equals m minus m, where m is the apparent magnitude and m is absolute magnitude. M is again in turn defined by this, where f is the flux of that distance source, and fx is a sort of calibrating that. In cosmological context, instead of this 10 parsec value, which gives uh, absolute magnitude of a luminous object, we use megaparsec, and the formula is modified into this formula when we calculate distance modulus. If you go on looking for astronomical measurement of distance modulus, you will see that it is 5 log 10 TL plus 5 and etc. This 25 factor comes because we change in cosmological model from parsec to megaparsec. TL is called the luminosity distance. I'll talk about it in a moment. What is a standard candle? A standard candle is basically a bright object, and we expect it has to be a very bright object because we are expecting to measure very distant sources of light, where standard method of parallaxes and etc. are not much used. So these are very bright objects with a standard luminosity. That in turn help us identifying that object as type 1a supernova from the light curve. And since the luminosity of an object, or rather the flux we receive from it, decreases with increased distance, it should in turn give us a measure of the distance if we know that there is sitting an object with standard luminosity. What we observe apparently can be then be calibrated with the standard one, and we can get a distance measurement. Okay. Distance modulus, pardon me for this extra line that I have already defined. Suppose that we are at the origin and at present moment, that is t equal to t0, and we observe some, again, there is slight typo, a light that was emitted by standard candle at some r theta phi coordinate. These are co-moving coordinates, of course, and these are moving with universal expansion at time t equal to t. In general, the light will be spread over a sphere of area 4 pi sk r square. Again, why not 4 pi r square? 4 pi r square is a standard formula for a surface of a sphere in Euclidean space. That is a flat space with no curvature. But if the universe has some curvature, then we have to use some general formula. You can check from the format of sk that without any curvature, it reduces to the standard formula. Anyway, so for an object of luminosity L, we should observe the flux F equal to L by D. But the universe is expanding, and the time interval between the photons change when they were emitted and when they are observed. The redshift factor creeps in. So finally, we get the flux formula like this. And if we try to write this flux formula like this, we have to define luminosity distance as Dn equal to skr 1 plus jet. Okay, so this is the more formal version of supernova curve. As you see, in a universe which expands with a constant rate, these points should be distributed linearly, but they are not. As we go on to the higher redshift, they tend to sort of come down, and that happens because at first we have defined apparent magnitude with the luminosity distance with a negative sign. So whenever the luminosity distance is a sort of, we expect that in an accelerating universe, this should actually come down rather than going up because they appear brighter. Anyway, this is actually an Union 2.1 compilation of supernova data from Supernova Cosmology project, and you can see from these figures these different colors for different surveys. This is basically a compilation of many surveys. And also, please keep in mind that in the lower redshift region, there are far many more samples available. So this suggests, this is the primary suggestion we have, that we live in an accelerating universe. And this is a fit for lambda CDM model, actually. That model that considers that we live in a universe with a small, very small indeed, cosmological constant, as a result of which the universe is accelerating, and the fit is reasonably good as we can see from I, but there are more to it. I'll come back to it later. Now, how do you do supernova statistics? Very standard practice. I have elaborated very briefly. There is going into the very details is beyond the scope of this talk. There are basically two approaches. One is the Bayesian approach, and the other is the classical maximum likelihood estimate, that is MLE method. These differ more or less in how we pose the question itself. In the classical method, we have a model with some pre-parameters, and we have a set of data. We try to fit the model with the data and obtain the best fit parameters. And also, additionally, we try to have a measure of how good the actual fit was. Bayesians like to pose the problem in slightly different way, that they sort of find out the relative fit of different models. Given a particular data set, which of these models will fit these data best? That's the Bayesian approach. For today's lecture, we'll concentrate more on the maximum likelihood estimate. So they define a chi-square function with, I have elaborated the chi-square with the apparent magnitude. This is the theoretically obtained apparent magnitude depending on the model. The theta is the measure of model parameters. The theta can actually contain many parameters. The model can have as many as 3 parameters you may like. These are observed apparent magnitude, and these are the errors associated with the observation. For a good fit, for a reasonably good fit, what do you expect? It is very clear from here. In the reasonably good fit, this theoretical value should not differ from the observed value by more than the deviation in the observation itself. So this should come for n points in observed data points, which come chi-square equal to 1, or per degree of freedom or per degree data point, chi-square should be very close to unity. That will determine a good fit. A more formal way of determining a good fit is to calculate this p value. If x is the best fitted value for the chi, for this x and for n degrees of freedom, the p value is calculated, and if p value is greater than 0.001, the fit is said to be acceptable. But of course, you can vary this 0.001. If you are to be more accurate, you can take it to 0.0001, or if you want to relax the criteria a bit, you may consider 0.005. But 0.001 is a very standard acceptability criterion. Now, we are going to see some very interesting thing that has become of late a very standard practice in fitting supernova data. Mostly these points are found in this paper by Vishwakarma and Narlikar, and there are some cross references as well. The main problem that they observe is that there are thousands of cosmological models present here, and I will at the end try to elaborate why there are practically thousands of cosmological models. People always try to fit these models with just lots of pre-parameters with the given data and estimate the parameter values. The crucial thing to note is that in most of the cases, they end up only estimating the parameter values. That means they are assuming that their model is correct. For a well-established model, this is a very good practice, nothing serious. I mean, if you know for sure that your model will work, then you go on, fit your data with the observed data, fit your model with the observed data, and estimate your parameters. That's fine. But when you are not sure about the validity of your model itself, you don't go on fitting the data and estimating your parameters. You should be concentrating more on the goodness of fit. In fact, the Bayesian method is better because they sort of give you an idea of relative measurement of fit, which of the models fit better. But even if you do the classical method, you should more concentrate on how good your data actually fits with your model. Even the works with the standard model, which is supposed to be a very good fit, begs for attention. For example, this Astier et al. Paper, it fits the standard model. Now it assumes a priori that there is 23% of dark matter and 72% of dark energy present in the universe, then go on fitting the parameters, etc. Now again, this is a priori believing in the model and only estimating the parameters. Does they show a goodness of it? Well, they do. They do, and the fit is actually good. But herein lies the problem. They use a chi-square function like this. And notice this sigma int square. This they called an intrinsic error. And then they sort of do a very interesting thing. After fitting the model, they go on varying this sigma int until a good fit is obtained. This is a very astonishing kind of statistics. I mean, there is every bit of possibility that your model will fit the data with reasonable accuracy if you have such kind of freedom. This has become a trend. And after this Astier paper, these, for example, Amanullah, Ghose, and etc., they do the same thing. Now, these papers, they are not just stray papers; they are landmark papers. These are, for example, this Amanullah paper. It is basically the Union 2 compilation of the supernova data, and hundreds and thousands of papers refer to their estimate for whatever work they are doing. So these are landmark papers, but yet they are having this ambiguity, that they have this ambiguous term of sigma in it, and they keep on varying this at their will unless a very good fit is obtained. If that is done, even if one obtains chi-square is approximately equal to 1 degree of freedom, there are valid questions. For example, of all the Friedman models, FW models, reduced to MT equal to this formula at very low redshift. Yet, isn't it more reliable to use independent measurement of uncertainties from the data itself? Collect the sigma intz from the supernova data itself and take it into account rather than randomly varying it until you obtain a good fit. The above approach, that means varying sigma int and etc., is perfectly valid for a well-established model. That means if you are certain that your standard model works, you go on varying the sigma in it and standardize your error or something. But in our case, we are yet to establish the standard model from scratch. Remember that supernova data is the only independent confirmatory test for existence of dark energy that is accurate in universe. The other experiments, notably the CMB experiments, they establish the flatness of the universe, although that also has some issues. They don't really establish the flatness of the universe. Rather, they see that our universe is indistinguishable practically from the flat universe, etc. But I'll not go into the detail of those things. The point is that supernova data is the only independent confirmatory test for the existence of dark energy. All the other signs are quite indirect in nature. Worse still, there are reports of conflicting within supernova data analysis, and this paper will deal with that. I'll give the reference, but today I'm not going into that detail, etc. I'll give you one example, though, from the Vishwakarma paper. They have worked out this constitution data by Hicken et al., etc. They have fitted a model with the supernova data, the standard model, and have worked with it. But as I mentioned before, it has become a standard practice to estimate the parameter and not to concentrate on the goodness of it. When that is taken into the account, and the authors Vishwakarma and Ehrlicher actually did that, they saw that the lambda CDM model does not fit the constitution data well, and in fact that can be ruled out with 99% confidence. That's astonishing. So why not keep the situation open? Why not consider alternatives? Are there alternatives? Well, yes. So let's briefly discuss one of them. Now, this is from the paper Colin et al. In 2019, and one Souvik Ghose is involved in this work, who has done other works as well on similar lines. But today I am going to discuss the findings from this paper as briefly as possible. In real universe, we have peculiar velocities. What are peculiar velocities? These are local velocities on top of the cosmological expansion because there are local inhomogeneities and anisotropy. For example, our local group of galaxies move with respect to the expanding universe at 620 plus minus 15 kilometers per second now towards L equal to this. There is no need to get into the details of this treatment. This is a direction of CMB anisotropy. It is a standard direction of CMB anisotropy, which is visible from recent Planck and WMAP data, etc. Towards this direction, our local galaxies tend to move on top of the universe expansion with this kind of velocity. And there are studies that suggest that peculiar velocity does not fall off as 1 by r in lambda city universe. And there are studies confirming it up to at least 300 megaparsec. Is there any possibility that we are observing these effects by chance? Well, computer simulation says that odds are less than 1% against this happening by chance for velocities exceed 250 kilometers per second and for redshifts greater than z equals 0.03. So we do have some considerable peculiar velocity, and if we consider that, we are not really in the CMB rest frame, that is not really in the co-moving frame, we are rather tilted with the co-moving frame. But the cosmological observables are formulated in the CMB rest frame. So how to take care of those when analyzing supernova data? Supernova data have to be corrected. And in fact, the surveys like JLA or Indian 2.1, they correct the supernova data for these peculiar velocities. But let us see these corrections. These are these velocity corrections. And the Z-hel means the heliocentric frame we are living in. So they have converted the data, they have corrected it from our heliocentric, for our heliocentric frame. And these are the corrections. See how the correction values. And notice that after a certain time, the correction becomes 0. So they assume that after a certain point, it is around redshift 0.06. These corrections converge. And notice that there are some wayward points here, here, and even in this region, here, etc. So they actually assume the convergence at 150 megaparsec. But remember, we have evidence. There are studies, maybe they are debatable, but there are studies confirming that there are peculiar velocities not falling off up to at least 300 megaparsec. Figure 11, forget this 11 thing, it just refers to the previous figure, shows that the corrections are made up to z equal to 0.06, mostly 0.06. Then there are some stray corrections, but mostly up to this point, 0.06. Then the data converge. From where do they correct this? They correct this from Hudson et al. Survey. Curiously, this survey has a maximum event of z equal to 0.04. Yet they are correcting it up to z equal to 0.06. And it is unclear how their corrections are applied. Beyond this limit, there is an uncorrelated C sigma z 150 kilometer per second inverse, but they do not justify that as well. This assumption is questionable. There are persistent claims that there is some sort of a dark flow extending beyond several hundred megaparsec. And although these issues are debatable, but there are claims. The anisotropy is there in the JLO catalog itself. See the JLO catalog. These are the data points. These are the supernova they take into the account. And see how they are distributed throughout the universe. And see these low redshift surveys, cluster of points in this portion of the space only. There are far more points in this hemisphere rather than this hemisphere. So there is an isotropy in the JLO catalog itself. Out of 740 supernova samples, 551 one are in the hemisphere pointing away from that CMB dipole direction that I was talking about, this direction. In view of the Hudson paper, it seems that out of the 746, 32 are in the lower hemisphere only. So whatever compilation they have, it is very, very, very anisotropic. So when fitting supernova data, the model information comes from equation 2 through DL. Remember that new equation that contains DL, that luminosity distance. The model information comes like this. DL is given by this formula. This is the Hubble value at present epoch. This is Hubble at a particular redshift. They have to be integrated, but from the Friedman equations, we know that Hubble are like this. These omegas are density ratios. For example, this omega m is density of matter divided by the critical density that has a standard value these days. This formula is for standard lambda CDM cosmology. So that's where the model thing kicks in through the luminosity distance. For JLA analysis, Colin et al., when they have analyzed the data to see whether there is an acceleration or whether the peculiar velocities are responsible, they call it bulk flow for the apparent acceleration. They use a salt scheme of parameterization. This is something adaptive light scheme, light curve test template 2. This is the parameterization they use. Here, alpha and beta are constant, and x1 and c are related to light curve shape and color correction. They are not considered from the standard formula 5 ln n, etc., from where the model hypothesis sort of creep in. So they sort of try to use a model independent parameterization of distance modulus. Now, instead of choosing any particular model, they consider a Taylor expansion of luminosity distance. Yeah. And the cross reference is given, so you can actually go to the Visser paper, which has a detailed discussion on how this formula was derived. Anyway, this Q here is the deceleration parameter, and Q0 stands for the present value. This J0 is called Chap parameter, and if you go to the higher order chance, you will encounter something called snack parameter. To look at whether there is any dipole term present is the acceleration parameter, deceleration parameter Q. The parameterized Q like this. This is the monopole term, talking about the standard acceleration or deceleration, whatever. And this is the dipole term, which is not considered in fitting standard models of cosmology with the data. This is something new. They consider 4 cases. These X actually gives the redshift and dependence and direction dependence. See this unit vector. They consider it along the direction of that CMB dipole direction. That is reasonable, actually, because most of the bulk flow data says that the bulk flows are restricted within 40 degrees of those CMB dipole direction. Also, you may question this Taylor expansion. You may say that whether it works at higher redshift, particularly redshifts close to unity, but they have actually checked it whether their DL gives the correct result, and they have found that up to the limit of supernova data, the observed limit of supernova data, their model works well. The Taylor expansion is indeed valid. There is no visible discrepancy between the standard calculation of luminosity distance and this parameterization. So they consider 4 different kinds of F and try to fit the data. Given the anisotropic sky coverage of the database, it is difficult to find a particular direction of the dipole, so they consider, as I mentioned, it to be along the direction of CMB dipole. And most of the bulk flow they are considering are within 40 degrees of the CMB dipole direction, so their choice is quite justified. The author then proceed with the standard maximum likelihood estimate that I elaborated briefly. They find having a dipole component in Q improves the fit. How do you conclude that it actually improves the fit? Well, there are things. For example, the p value I mentioned, and what they use here is uh, a ratio test. The lower values are better fitted. A non-accelerating model is strongly favored from BIC. What is BIC? BIC again is a measure of goodness of fit, and it is called Bayesian information coefficient, and lower BIC is favored. The model independent evidence of acceleration is established only at 1.4 sigma level. There were claims that the model independent acceleration has been established in greater than 6 sigma level, but they found it to be only at 1.4 sigma level. Also, they found that presence of a dipole component is favored at 3.9 sigma level in the direction of CMB dipole. Conclusion: they conclude that there is a strong possibility that the apparent acceleration is an artifact of the existence of local bulk flow. That's what they are considering after all. These are their results. As you can see, when dipole is considered, this log max L max value, the lower is better, actually goes down from minus 189 from 208 and 205 here. This is the no tilt where no dipole, and this is a model with no acceleration. The tilted universe has the best fit like this. And see, the dipole term is much more significant than the monopole term. The BICs are here. That also favors the dipole term to be present in the model. These are the sigma z where they have left sigma z floating instead of hand putting the sigma z at 150 megaparsec, etc. What was done previously in JLO cataloging, they have kept the sigma z floating and fitted the model. Here again, a considerable good fit has been obtained for the presence of dipole term. And this is the graphical representation of the dipole and monopole in different confidence contours. So what do we stand? The simplest model is the one with the cosmological constant, which has an equation of state fixed at -1. The standard model is very successful. Despite of our criticism here, the standard model is very successful. It has successfully predicted CMB results, and there are structure formation models, very clear-cut models. There are clear-cut indications, at least it is claimed from CMB observations of information and structure formation theory being correct, etc. But no theory is there to predict the ridiculously small value of a cosmological constant, what is demanded by the observation. In fact, the discrepancy is, I believe, if I can remember correctly, is 10 to the power 60 order of magnitude, and etc. This is a gigantic mismatch. Also, there is no justification why, at the present epoch, the mass density and the dark energy density is at a comparable level. Remember that matter density falls as the universe expands, but the dark energy density, if it is a cosmological constant, remains preserved. And in less universe, dark energy start dominating. Why? Why we should exist in such an epoch that is called some sort of coincidence problem. Needs a bit of fine tuning, which is not very comforting to physicists. No theory with a very, very, very fine tuning is a very comforting one. Now there are dark energy models where instead of considering a fixed dark energy lambda, they consider a dynamical model of dark energy. Most of these dark energy models are based on scalar fields, but they do not solve this problem. Firstly, they lack the predictive power. Friedman equation with the Friedman equations and the Lagrangian of the scalar field, almost any scale factor can be modeled with some sort of designer uh, potential, scalar field potential. And remember, there is no theory giving us an idea of what sort of scalar field potential we can choose. There is absolutely no restriction. You can go on choosing whatever scalar field potential you may like. As a result, you may create your model universe to have a scale factor of whatever you desire. Then the models are degenerate. There is another field like scalar field, which is inspired from string theory called tachyonic field, and it can be shown that whatever may be your scale factor, that can be modeled either with a scalar field or with a tachyonic field. So at least there are two models corresponding to any scale factor you come up with. Then the potentials, they don't have any field theoretical justification. Most of them are not renormizable. Lastly, observation do not even demand the dynamical dark energy. There is no observational suggestion that we need a dynamical dark energy. We only tend to discuss dynamical dark energy model to avoid the fine-tuning issues with the cosmological constant. But then it seems that if we go on discussing the scalar field models, we have to fine-tune the model parameters to obtain a good fit, etc. So the fine-tuning problem is not gone. It's been just shifted to some other level. And most of the other phenomenological model with varying T and varying T and etc. Most of them can be mapped into some scalar field model. So this is a prevalent model throughout the dark energy models. The prevalent, all the troubles are prevalent. Nothing goes away if we consider instead of a cosmological constant in dark energy, evolving dark energy. Where do we stand then in alternative situation? I have noticed that Colin et al., although they considered a direction-dependent function like FZS, they do not really discuss in detail the exact role that is played by FZS. There is some ad hoc reference to one particular model, but there is no detailed discussion of this F thing. Also, the salt scheme they actually use the salt 2 template, but this template has issues. There are other methods of model independent parameterization, for example, MLPS, and there are substantial mismatch in salt MLPS. Also, there has been suggestion that the salt mod scheme does pick up some model dependence, and they are not completely model independent at all. They have claimed that QM can be rejected for more than 1.4 sigma confidence. But actually, they have, while they claim that QM is, that means the monopolar accelerating term, whatever acceleration we call in standard models, that is accepted only at 1.4 sigma level. But what they have actually found that it can be rejected beyond 1.4 sigma, but only in presence of QD. Remember, if the QD is not there, then their theory just falls apart. There is no suggestion that even if the QD is not present, still the model, the acceleration of the universe has only 1.4 sigma. There are, however, other alternative approaches. For example, there are papers which show that Thomson scattering may be responsible for the observed acceleration to some degree. And there are lots of work with void models considering local over or under density because of existence of a bulk inward or outward flow. That means, simply put, it suggests that we maybe are located in region of local over density or local under density. There has been lots of work. Moreover, there are issues with the standard candle itself. There have been studies challenging the evolution of supernova, type 1A supernova luminosity and extinction of supernova light by dust, etc. They are not well established theory, but there have been suggestions. So overall, there are lots of theoretical as well as observational issues, particularly bad practice of statistics going on around supernova data, and perhaps we are putting too much emphasis on the standard model of cosmology. However, standard model has its own success, and based on these issues, we are still in no position to altogether rule out the standard model itself. At best, we can keep the situation open. Thank you. These are just the references.
Thank you, Souvik.
Yeah.
There is one question. You can see the chat box. Shobhashachi Rai has asked one question.
Yeah, okay. See, the thing is, I have not yet investigated the dark flow papers very well, but it has something to do with the dark matter flow. Whatever bulk flow I was discussing was because of the visual overdensities and etc. This dark flow is related to the dark matter densities, but I have not checked the details of the dark flow in the paper. So maybe I'll give you some references and I'll look for it further.
Any other questions? You can unmute yourself to ask the question, no problem, as the talk is over. Arinanda, you can also unmute. Okay.
Souvik, have you gone through the
Any questions?
papers by Rubin?
Considering which thing, I have downloaded a good deal of paper. I think the Rubin paper is also here. I can check. Could you please tell me what actually the Rubin paper discusses? I tend to forget the name of the author and etc.
Actually, Rubin et al. They actually raised a few questions. Questions means they have their view that these.
Oh, okay. I understand. You are referring to the paper which actually I think challenged the work by Souvik Ghose and etc. Right?
Right.
They have recently come up with another paper answering the question.
Well, but while answering their questions, now the situation has changed quite a bit.
Okay.
Now they are claiming that okay, the accelerating situation is just 2.8 sigma. It is just less than 3 sigma.
Okay. Yeah.
But what about the dipole claim? That appears to be due to non-inclusion of the solar system moment.
Okay. Actually, their paper, as I talked about it also, their paper has some issues. For example, that the F function, they completely sort of take it in an ad hoc way and then never discuss it at all. Amazing.
I think have you gone through the paper by Vishwakarma and Narlikar?
Yes. That is a far more interesting paper.
I think that paper is a better one. But one question is that you have mentioned that they are considering sigma intrinsic. They are heading sigma intrinsic.
Yes.
What is the range of the sigma intrinsic?
What is the range of the sigma intrinsic? Actually, the sigma intrinsic thing I got from Vishwakarma et al. They have suggested a few data. I have not cross-checked the data itself, but it seems that they keep on varying the data, the sigma intensity in an arbitrary way before the good fit is obtained. More than the range, the interesting thing is, please.
Sigma intrinsic, the range is very important because suppose sigma intrinsic you are varying in a reasonable range, then at the range boundary, the proportion of dark matter, dark energy may vary a little bit, but it will not wipe out dark matter or dark energy situation.
Okay, that I will cross check, but
range of sigma intensity is more important point. That needs to be
Yeah, that may be true. That may be true. I can understand that if they are not considering an unusually high range, there still may be justification of varying it. Still, I don't think it is a very good practice to obtain a fit like that without justifying why we are varying. And
definitely, definitely.
because okay, the problem with these papers is in most of the time it is very difficult to cross check the algorithm they use, the data they use, etc. It is very difficult to cross check for me. I do not have the computer expertise as well as the resources. I mean, most of the time it is not even the laptop.
No, most of the most difficult part is data. You don't have the data, access of the data.
Yeah, that I actually skipped in the Colin paper. Why they have considered JLA and not the pension data, because the pension data is not publicly available at all. What they are doing, they are not disclosing how they are fitting, what sort of corrections are made.
Right.
But most interesting, from that Colin et al. Paper, the bulk flow model. If you forget about that for this moment, there are a few interesting points. For example, the anisotropy in the JLO cataloging, and secondly, the correction itself. If the
No,
source,
if the anisotropy due to solar movement of the solar system, then this is not a
okay, and what about that point regarding uh, the ad hoc correction they are assuming about the peculiar velocities, the Hudson data, if it has a maximum event of z equal to 0.04, how are they correcting for 0.03?
that I don't know.
So strange things. That's why I kept it open. Actually, it's very difficult for me to comment at this point whether these are very novel studies or something. But uh, strange things are going on. Of course, we cannot rule out the standard model, but there are issues.
Yeah, obviously there are issues, but I don't think the people are not fooled. So when they are accepting standard model, they have some strong reason for that.
Yeah, definitely. Because I mean, here we are only discussing the supernova thing. The standard model comes up with a very good theory of structure formation and explains the CMB, etc. So they cannot be ruled out based on these things.
Yeah, CMA anisotropy, other the finer details, those are very important and interesting. So
Yes, I'll try to
any
I'll try
alternative
to
effort has to explain those things.
yes. I'll try to look at the CMB data at some time, because both in Nardika paper and some other paper as well, there seems to be some issues with the uh, CMB data as well. Some conflicting results. That does not mean the CMB data is wrong or something, but there are issues in the CMB data as well. For example, this anisotropy thing.
Okay, thanks for the nice talk.
Okay. Okay. Thank you. Over to Arindam.
Souvik, in chat box there are more questions. Okay, you can look at it.
Okay. This study with
One more
summary.
question.
Okay. If we discuss the dynamical dark energy models, are there any alternatives in the present acceleration, also the intrinsic error? Or can you please? Okay. Uh, there is a question from Anirban that if we discuss the dynamical dark energy models, are there any alternatives which explain the present acceleration, etc.? And the second question is the intrinsic error of the supernova data. Can you please elaborate on it? I think from our discussion or Anirban, you have got some idea about the intrinsic error. Regarding the question of dynamical dark energy model, I would say that okay, models, most of the dynamical dark energy models can indeed be mapped into scalar field models, but there are models you are familiar with, for example, the unmodified gravity models, which are uh, not parallel to the scalar field models. Although, if you consider FR gravity only, all the FR gravity models can be mapped into the equivalent scalar field thing. But the crucial thing is, if lambda CDM is not ruled out, why should we go on considering dynamical dark energy model if it does not give us any substantial advantage over lambda CDM? Lambda CDM is simpler. It has only one parameter in that sense. So why should we go on searching for it? The only thing undesirable in lambda CDM model is that fine-tuning issue. As I have discussed, that that thing does not go away with the dynamical dark. So yes, the situation is open, but that's the case. Now the other question is by Roger Baser. The study is summarized here based on the supernova data. What AGN data do tell about the accelerating universe? Okay, sir, I do not have any knowledge about the AGN data telling us about the accelerating universe. Perhaps Ornahuda might be able to answer it, but I do not know if the local surveys do play a role in determining accelerating universe in that way. But okay, AGN in that sense, maybe, but I am not familiar with the AGN X-ray data playing any role in describing accelerating universe. So, do you have any suggestion over this?
No, AGN is not a standard candle. That is the problem. So you cannot measure the distance.
Yeah. Locally, I think yes. Locally, I think parallax method and etc. can come in handy in case of an AGN, but
AGNs are far away, so it is not possible. You don't have a standard candle, so you cannot measure the distance.
Yeah.
So,
and I think the other method of measuring distance, for example, parallax, simply does not reach out to that level where we can have an evidence for accelerating universe.
at such large distances, parallax method is not applicable.
Yes, exactly. So that's it.
Okay. Is there any more questions?
Amazingly, Samrat doesn't have any question.
Then, if there is no more questions, then from CRAGA, we give a big hand to Dr. Souvik Ghose because he deserved for adding some more questions on our confusion set on accelerating universe.